Alright guys, welcome back. It's final exam guy, and I decided to go through a second calculus final exam just because it's a tad harder, but still not that difficult. Just for extra practice to make sure you're super ready for your exam. Sorry about that. Just a few things I want to say. I'm going to put specific questions in the descriptions so you can skip directly to them if you need help with them. Please support me by subscribing to my channel and keeping an eye out for my future videos. I might be able to help you in your career, school careers, and engineering if you're going into engineering. So I'm going to be doing a lot of mechanical engineering problems and maybe other fields as well. So this is an older exam, 2015 from college here in Canada. Let's go through it one question at a time. So for the first question, we have find each of the following limits. Please show all your work and give exact answers, no decimals. Alright, so the first one is, so we're going to find the limit as x squared, as x approaches 2, of x squared minus 9x plus 14 over 3x squared minus 6x. Alright, the first thing to do, as always, is to plug in the approaching value into your function. See if you get a real value. So if we plug in 2 in it, we get 4 minus 18 plus 14 over 12 minus 12. So what happens here is that we get 0 over 0. So what do we do in this case? We gotta factor this. Like we can't submit this as an answer. We can't say does not exist. That will be wrong, 100% wrong. So let's go ahead and see what we can do. We can manipulate this equation so that we get something simple. I call it the bare bones. And then we can plug in our x value and we should get a real number. So right away off the top, we can see that the numerator factors easily into x minus 7, x minus 2. Try to factor yourself. You guys can learn by factoring. Algebra is very important in this math course and future ones. The denominator also factors to this right here. So obviously we can see that we get some cancellation here, and then we have a final expression of the limit as x approaches 2 of x minus 7 over 3x, which is 2 minus 7 over 6. It's negative 5 by 6. That's our final answer for A. Easy enough. Let's move on to question B. Question B says the limit as x approaches 1 of root x squared plus 48 minus 7 over x minus 1. Like I said in the previous final exam, there was a root in the numerator, which we don't like in math usually, so we'll take care of that, but let's just try to plug in our value of 1 and see what we get. So we get 1 plus 48 root minus 7 over 0. So we get 0 over 0 once again. We cannot submit this as an answer. We can't just go and say it does not exist, because that's wrong. We have to see first if we can manipulate this, which we easily can. Just scroll down a bit. Let's multiply this equation by the complex conjugate. That's how you get rid of the root in the numerator. So let's go ahead and do that. Minus 7 over x minus 1 multiply by the complex conjugate of the numerator. So x squared plus 48. So you just reverse the sign of the minus sign, multiply by the same on the top and bottom. So guys, do this yourself. Please, if you're writing this down on paper, work this out, because I'm writing the direct answer here to save some time. So the limit, we end up getting the limit as x approaches 1 of x squared minus 1 over x minus 1 times root x squared plus 48 plus 7. And from then on, we can see that this just reduces to x plus 1 over x squared plus 48 plus 7. And of course, the limit as x approaches 1. So we would plug in our 1 now and see what happens. So we get 2. So we have 49 in here. Square root is 7 plus 7 is 14. So 1 over 7. That was that. Alright, question C, saying that the limit as x approaches infinity of 17x to the power 5 minus 3x 8. I'm going to show you two ways to do this, because in case you forget one, this is a limit as x approaches, it's negative infinity. So the two ways to do this: number one, compare degrees of each polynomial. Remember how I said that if you compare the exponents of the largest exponents you can determine whether the limit's going to infinity, to 0, or some other value. So let's take the numerator. The highest exponent term is this one here, and the denominator, the highest exponent term is here. So when the exponents are the same, it's just you divide the coefficients by each other. So the answer would be negative 3 by 13. And the second way is the more mathy way to do it. So you would divide by the largest exponent in the equation, which is negative x to the power of 8. So if I want to go ahead and pull that out from everything, well, divide everything by that, I would get 17 over x cubed minus 3 over 13 plus 4 over x. Alright, and now what happens if you plug a negative infinity over inside? You would actually get, this term would go to 0, because 17 over a really large negative number will go to 0 as it approaches negative infinity. This one would go to 0 as well. And then we will be left with negative 3 over 13. Same result, two different methods. Alright, let's move on. Alright, so we arrived at another continuity problem, piecewise function. I'm going to try to explain this as best as possible so you understand. It's a bit mumble jumble when you first hear about it, but it makes sense after a while. So find the values of x where the following function is discontinuous. For each value, clearly state why y is discontinuous by using the definition of continuity at a point. Alright, so say we have a graph with some sort of function that looks like this. Points. Continuous means the graph does not break. There's no break in the graph. Here you see that there's a break over here, and it happens at this point here. So this point is the point where it's discontinuous. So if you look here, we have a function that from negative infinity to before 1 is, the function is 1 over x, and between 1 and 2 it is x, and if it's greater than or equal to 2, it's 3x squared minus 11. So points we're going to have to evaluate to see if they're discontinuous are points in these ranges. So I mean, 0 is a point, popular point, and this, you see that we got 1 and 2. So we're going to evaluate these 3 and see if they're discontinuous at any of these points. So if we start with 0, we're using an x value that's below 1, so we're going to have to stick with this function, right? So if we try to plug in 0 here, we get 1 over 0. And that, by definition, is discontinuous.
Whenever you're dividing by 0, there's an automatic break in the function. It's going to be discontinuous at point 0 because the does not exist. Okay, so now let's move on to 1. Where are we at if we're using 1? What we're gonna do when we have a value like this is we're gonna approach it from the left and we're gonna approach it from the right. So what I mean by that is that, let's say I have a graph here, sorry, 1, this is 1, and approaching from the left means we're going to come by this way and follow the graph, follow the line. So the limit of the function as x approaches 1 would be this value here. Right? Get it? And then if we're going to approach from the right, we're going to follow the trace of the graph, and the limit on both sides is the same value, so it's continuous at this point. You get it? So like you see on the top graph, if I'm coming from the left, we'll follow the trace, see that it approaches this value when you approach 1, but if you come from the right, the value is different, it's higher. That is the definition of the limit. That is the definition of continuity. That's how you check whether it's continuous. You come from the left and right and see what happens. So if we take negative, we approach 1 from the left, we'll put a negative sign here. That means we have to use this function because we still didn't arrive at 1, but we're approaching 1 from the left, so we'd use this function. So if we plugged in our 1 over 1 here, we would get f of x is equal to 1, and then we check the other side, which is the positive side. So we would be approaching this way, so we would have to use this function because we're going to arrive at 1 from that side. So we would use x, and we plugged in 1 into x, we get 1. So they're the same. So on the graph, this is not the graph of the function in itself, but this would, the line, there would be no break of this line. It would, as you approach 1 from either side, it would be continuous smooth line. So obviously it's continuous at 1. And now we do the same thing for 2. We'll approach it from the left and we'll approach it from the right and see what happens. Alright. So if we were to approach -2 from the left, which function will we have to choose here? We can't choose number 1 because that's only for below 1. If we chose number 2, the second function, we would see that we can approach, if we are in this range, we are approaching 2 from the left, because we're going to be just below 2, so we're coming in from the left. So we would choose this function and then plug in our -2. Sorry, it's not -2, it's just 2 from the left. We would get 2, and then if we coming from the right, we would use the third function, because I guess you can just see it as the greater sign is that way. You're coming towards the point of the greater sign, so you're going to use this function, which is 3x squared minus 11x. And if you try to plug in 2 here, you would get 12 minus 22, and that will give you -10. And these two are not the same. So you know that there's a break at the point 2. So what this means is that at point, I don't know why I was drawing 1 on the opposite side, that's wrong there, but we'll just say my example was with -1 before. So I got my 2 over here that we're evaluating. If we come from the left, yeah, we arrive at this point, 2. If we approach from the right, something happens with the function, it goes crazy, and it ends up stopping there at -10, and these two values cause a break over here, and leaving us with discontinuity. And you put this on the exam, you will get good marks. that's what we have, and you can check the first exam too. I wrote the definition of continuity. It's the limit of our function as x approaches a, some value a, has to equal plugging in a into the function. And I encourage you to see how this relates to all this stuff over here. If you can't figure it out, please comment below and I will do my best to further elaborate for you. Let's go and do the next problem. Alright, so question 3 says find the first derivative of each functions. Answers do not need to be simplified but should be expressed only in terms of x. Alright, so there's 4 of them to do. I listed the first 2 here for now. Let's go ahead and evaluate each one. So let's go to problem A. It says that y is equal to tan of sine of x plus tan x sine x. Alright. You should be able to look at this and say chain rule. You should be able to look at this and say product rule. Chain rule, I want you guys to learn a method that you can just easily find the chain rule within 3 seconds. Like literally. Just say it with me as you do it. Let's call this outside, inside. Chain rule is always going to be like 2 functions, one inside the other. So we can go ahead and say the derivative of the outside, that's what it will be. Sorry. Yeah, derivative of the outside. So derivative of tan is secant squared. And you leave the inside alone and you multiply by the derivative of the inside. Always remember that, guys. Derivative of the outside, leave the inside alone, multiply by the derivative of the inside. One more time. Derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Okay? And now the other one is the product rule. I had said this this thing you memorize as well. Product rule, derivative of the first, secant squared x, times the second, plus the first, times the derivative of the second. So, derivative of the first times the second, plus the first times the derivative of the second. That's exactly what you have here. So just remember those 2 sayings. One for the chain rule, one for the product rule, and there's also one for the division quotient rule, which we'll do in the next problem. Okay. So problem B is y is equal to ln x squared plus x plus 1 over x squared plus x plus 1. So here we have the quotient rule, and it's another saying you're going to have to remember. Like I said in the earlier video, I took this class like 5 years ago and I still remember these sayings. I didn't have to do a refresher or anything. They're just in my mind for the rest of my life. Did them so much. Alright. So, sorry guys. Sorry about that. The quotient rule, you're going to do low. We'll call this low. We'll call this function on top high. So low d high, d as in derivative, d high. So derivative of the, well, I'll just write d dy dx here of the high ln x squared plus x plus 1 minus high d low. Okay, all over the bottom squared. So I'm going to say it low, low, d high, minus high d low all over the bottom squared. I forgot that. Low d high minus high d low all over the bottom squared. Okay, so let's evaluate the derivatives that I had written there, dy dx. So x squared plus x plus 1. Now this is in brackets. So when it's ln, it's just a little bit different than this. So you use derivative of the outside. You know the derivative of the ln function is automatically 1 over x, but you're going to leave the inside alone over here. Okay, same thing, except you just it's a fraction, because it's a quotient, because we're dealing with ln. So derivative of the outside, you leave the inside alone at the bottom. Multiply by the derivative of the inside, so 2x plus 1. Okay, now minus x squared plus 1 plus x plus 1, and the derivative of that stuff is just 2x plus 1, and all that over the bottom squared. Just leave it like that, because it's way too complex to I mean, you could cross out you can't really cross out anything here, because you can't factor anything out in the numerator, really. I'll leave you as a challenge to try to figure it out, but the person who did this exam left it like that and got full marks. So let's move on to part C. Alright, so question C, part C, is saying that y is cotangent squared 3x squared plus 5x. Whenever you see like a squared like this, right after a tan or a sine or cotangent or whatever, I like to rewrite it like this, so you can see it better when you're doing the derivative. That means everything is squared, basically. That's all it means. So you got a lot of stuff going on here. You got three functions here, basically. You got, if I can write the functions in their simplest form, you got this type of derivative to do, you've got this type of derivative to do, and you got the the innermost function, which is whatever, 3x squared plus 5. So you got like 2 chain rules to do here. Like I said in the previous questions of the chain rule, we're going to start with the outside, then leave the inside alone, and then multiply by the derivative of the inside. So let's do that. Let's try it here. Okay, so I think I've been forgetting to write y prime a lot, but so I'll start doing that right now. So let's look at this function here. The derivative of the outside would be this x squared type of thing, because like we can say that all this is x, and we got this 2. So you know how we do the derivative of x squared? We bring the 2 to the front and we subtract 1. So let's do that. We'll bring the 2 to the front, leave the inside alone, right? Then multiply by the derivative of the next function, which is this one. And that derivative, there's a 1 here, right? But you can just omit it. Derivative of cotangent is negative cosecant squared. So you'd multiply by negative cosecant squared. And then again, you'd leave the inside alone as well. So it's a chain reaction, basically. And then you multiply by the derivative of the inside of that stuff. So 6x plus 5. I hope you caught that. It's I guess a cascading effect, like a chain reaction. So you start with the outermost function, which is the whatever is inside the bracket, to the exponent. You bring the exponent to the front, subtract 1 from the exponent, and leave the inside alone. So that's what we did. We brought the 2 to the front, left the inside alone, multiplied by the derivative of the inside, the next function, but left the inside of that next function alone, then multiplied by the derivative of that final inside innermost function. Rewatch this 3-4 times. I'm sure you'll get it. It'll just click. And after you understand this, any chain rule problem, well, no problem. You'll kill it. You'll kill it. All right. Question D. y is equal to sine of x all to the power of 3x. Alright, when you see some crazy function like this where the exponent is a variable of x itself, you gotta just throw in the logarithmic differentiation. So that's when you ln both sides, ln sine x to the 3x, because when you do that, you can take this 3x and bring it right here, and you can rewrite the function that way. So let's do it here. 3x ln sine x. Alright, so let's apply this, and now at this point you take the derivative of both sides. This is going to be implicit differentiation, because normally we're differentiating everything with respect to x, but suddenly we have no choice but to differentiate with y. So we do that differentiation 1 over y, because the differentiation of ln of something is 1 over something. But then you have to multiply by y prime, because it's implicit differentiation and you're forced to differentiate with respect to y. You're differentiating y with respect to x, so you have to tack on a y prime. We'll do another implicit differentiation problem later. Okay, so differentiating this side, it's a product rule. You can see that it's the product rule. So I guess we'll call this term 1 and this term 2. So the first, remember this, times the derivative of the second. So ln sine x is chain rule again. So derivative of the outside function, but what goes under is the inside function, which you leave alone, and then you multiply by the derivative of the inside cosine x. And then we're continuing the product rule, so it was the first times the derivative of the second. No, sorry, I even messed up. I'm gonna redo it because I want you guys to remember my saying. It was actually the derivative of the first times the second plus the first times the derivative of the second. So derivative of the first, that's that. We'll put some brackets here, times the second Hey guys, I messed up once again. You see, now you're gonna understand because I'm repeating it for the third time. Okay, derivative of the first. Okay, got it. Times the second. Good. Plus the first times the derivative of the second. Derivative of the first times the second. Derivative of the first times the second. Yeah, I'm not gonna edit this out, guys. This is raw. This is raw. Me having a brain fart at midnight my time. Alright, derivative of the first times the second. That's my mistake. I was taking the derivative too early. Derivative of the first times the second plus the first times the derivative of the second. 1 over sine x cosine x. Right? Got it this time? Good. The only step left to do is to isolate for this y value here, so we have an actual this y prime over here, so we have an actual derivative in terms of x. So if we multiply the both sides by y, we can cancel out the y over here, and we know that y was our original function sine x 3 to the power of x, so that'll always happen in logarithmic differentiation, where you have to this is a plus, where you're gonna have to multiply both sides by y, and then you multiply everything by y. So sine x 3 to the x. Alright, pretty easy stuff, huh? Let us move on. Alright guys, question 4 is asking us to find the limit definition of the derivative to find f prime of x if f of x is equal to 2 by x. You must use the limit definition. Alright, so this is one you have to memorize. The limit definition of the derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So this first term here means that you're going to put the original function in, but every time you see an x, you're going to add a h to it. And the second term is just the function itself divided by h. So let's rewrite this with our function inside. H approaches 0. So 2, you add your function, x plus h, minus 2 by x, all divided by h. You can try to validate this limit here right now. We plug in 0 for h, but you'll see that the denominator is a 0, so that's invalid. You have to continue simplifying this equation. First thing to note here is that we can make these two terms here common denominator. To make them a common denominator, I'm going to multiply the first term by top and bottom by x, and the second term top and bottom by x plus h. So you get 2x over x plus h minus 2x plus h over x plus h over h. And of course there's the limit over here, I forgot to put it. And this equals the limit h approaches 0, 2x minus 2x plus h all over x plus h. Using simple fraction rules, you know that you can put this in the denominator, so you'll get 2x minus 2x plus h over x plus h. Yeah, and then you would do here is you can see that this ends up becoming negative 2h over xh x plus h, right? Because we multiplied it out, and then we get that. And the next step would be to simplify further, and we get negative 2 by x plus h, because we cancel out the h from the numerator and denominator. And now we can finally evaluate, plug in our 0, and we get negative 2 by x squared. Simple enough. I mean, a lot of algebra, but you'll get good at it. So that concludes part 1 of the video, or else it's going to get too long there, so I'm going to upload the next part. And please guys, click the bottom right subscribe button and support me. I love doing this. This is really fun for me. So I'll see you guys in the next video.